Hello everyone, welcome to my channel. In this video, we are going to learn about data and signals in the data communications. So, one of the major functions of the physical layer is to convert the data into the format of the transmission signals, right? So, the data will be in the format of digital in the computer or any electronic device, and we have to convert that data into signals for transmission from one device to another device. So here the data may be of any format, like it may be of image or video or text format or an animation. So it may be of any format. So the data will be of any format. So that data must be converted into transmission signal in order to transfer the data, in order to communicate with the other device. Okay. So for that part, we are going to convert the data into the format of signals. Okay. So here, to be transmitted, data must be transformed to electromagnetic signals. Okay. So the data may be of any format, it must be transformed to electromagnetic signals. So both the data and signals that represent them can be either analog or digital type. So data and signals will be of two types, that is analog and digital type. So first of all, we will see what is meant by analog data and digital data. Okay. So here analog data means information which is continuous. Okay. So here the information which is continuous is called as analog data. The example is analog clock and speech. Right. So here the data will be in the continuous format. So here in analog clock, that means the normal traditional clock. Okay, so the shorthand will represent the hours and the longhand will represent the minutes. So here the data, based on the movement of the shorthand and longhand, we are going to denote the time. Right. So here in the analog clock, the time will be continuous. Okay, and the human speech. So his speech will be also in the continuous format. Okay, so the voice will transfer from the particular person and it will reach the audience, right? So the speech will be in the continuous format. And what about the digital data? It takes discrete values. So for example, digital clock data stored in computer memory. Okay, so in the case of the analog clock, the time will be here continuous, right? So here this is 4 o'clock. So the time will be like this. But in the case of digital clock, it will show that the time is 4 o'clock, right? So in this format, it will show. So here the digital data is discrete, whereas the analog is continuous, right? And the data stored on the computer memory will be in the digital format. Right. So we know that the binary bits are 0 and 1. So everything will be stored in the format of binary bits, that is the digital data in the computer. So in order to convert this signals from analog to digital and digital to analog, so we are using some techniques that we will discuss later in the upcoming videos. So in the analog signal, so by performing the sampling, we can convert it into digital signal format. Similarly, the digital signal can be converted to analog signal by applying the modulation. Okay, so we use the modem, right? So in the modem, so the digital signal will be converted to the analog signal, right? So modulation and demodulation, we are going to convert digital to analog here. So these are the two techniques for converting analog to digital and digital to analog. So similar to the types of analog and digital data, so here we are having the analog and digital signals. So analog signals means it can have infinite number of values in a range. Okay, so it will be having infinite number of values in a range, whereas in the case of digital signals, it can have only a limited number of values. Okay, so here the analog means the continuous format. So here the signal is in the continuous format, and it can have infinite number of values in a range. So the signal will go on. So the signal will transfer in the transmission medium. So when the signal is transmitting in the transmission medium, then it will be having a infinite number of values along the axis. Okay, so whereas in the digital signals it will be having limited number of values. So we know that in the digital signal, so the high represents 1 and low represents 0, right? So like this, the given digital signal will be having some limited number of values. So next one is the periodic and non-periodic signals. So both the analog and digital signals can be classified into two forms, that is periodic or non-periodic signal. So non-periodic is also called as aperiodic signal also. Okay, so first coming to the periodic signal, it completes a pattern within a measurable time frame, that is a period. So we represent the time as period in the data communications. Okay, so here in the periodic signal, the signal is going to repeat over a subsequent identical periods. That means a particular signal or a particular pattern will be repeating. It will be keep on repeating in a identical period of time. So here the completion of one full pattern is called as a cycle. Okay, so let us consider the sine wave given here. So here the sine wave is an analog signal, right? So this is in a continuous format. So here the signal is completing a time frame here. So here the sine wave is completing a pattern within a particular amount of time, and it is repeating the same pattern again and again. So here up to this part, so this is a one pattern. So this type of pattern is again and again repeating. So here it is repeating. So this pattern is repeating here 3 times in the given sine wave. Okay, so periodic signal means it completes a particular pattern within a time period and repeats the same pattern again and again. Okay, so this completion of the particular pattern is called as a cycle. So this is one cycle, and this is one cycle, and this is one cycle. Okay, so this is the one full pattern. So again it is going to repeat the same pattern, and it will complete here. Again the one full pattern is finished. So next one is the non-periodic signal. It changes without exhibiting a pattern or cycle that repeats over time. Okay, so here the non-periodic signal, so it is going to repeat it is not going to exhibit any pattern here. Okay, so it will not be having any particular, the sine wave is not going to finish in a particular identical period of time. So it will be in a different format. Okay, so the pattern is not going to get finished here. There is no cycle here. Okay, so there is no repetition of a particular pattern in the non-periodic cycle. So this is one example of the non-periodic cycle signal. So in data and signals, data is of two types, that is analog and digital format. Similarly, signals are of two types, that is analog and digital format. So here there are two types of signals, that is analog and digital format. So analog is again divided into two parts, that is periodic and aperiodic or non-periodic. Similarly, digital signals are of two kinds, that is periodic signals and aperiodic signals. Okay, so here the periodic signals are again divided into two types, that is simple and composite signal. Okay, so we know that periodic means, so the same pattern will repeat over time. Okay, the same pattern will be frequently repeating, and analog means the wave will be continuous. Okay, so here simple periodic analog signal. Okay, simple periodic analog signal is simply a sine wave which is traveling over time. So it is a continuous wave. So here the pattern will be keep on repeating, and the sine wave is continuous. It is a simple periodic analog signal. That is the example of the sine wave. So simple periodic analog signals. So the best example is sine wave. Okay, the sine wave is the most fundamental form of the periodic analog signal. When we visualize it as a simple oscillating curve, it changes over the course of a cycle. Okay, so here the sine wave cannot be decomposed into simpler signals. Okay, that's why it is called as a simple periodic analog signal. And In the case of the simple periodic analog signal, it is a simple sine wave. Okay, so it is a simple sine wave. Whereas in the case of the multiple sine waves, that is a composite periodic analog signal. So it will be in the given format. Okay, so this will be in the given format. So the composite periodic signal will be in this format. So here you can decompose the given composite periodic signal into multiple sine waves. But whereas in the case of simple periodic analog signals, that is a sine wave, so we cannot decompose this given sine wave into simpler signals. So next one is the peak amplitude. So we are having three parameters of the sine wave, that is the peak amplitude, frequency and phase. Okay, so the peak amplitude means it is the absolute value of its highest intensity proportional to energy it carries. Okay, so it is directly proportional to the energy it carries, and we can represent the amplitude of a sine wave as the peak. So in the given sine wave, so here the signal is high in this position. Okay, so this is called as a peak amplitude. Similarly for the signal with low intensity, so this is the peak amplitude. Okay, so peak amplitude means it defines the energy it carries. So normally in the electrical thing, so it is measured in the volts. So next one is the period. So it is also one of the parameter of the sine wave. So it refers to the amount of time in seconds a signal needs to complete one cycle. Right? So a period means it refers to the amount of time a signal needs to complete one cycle. So here in the given sine wave, so here the pattern has finished one cycle here, right? So again this pattern is repeating here. So again this is the second cycle and third cycle and fourth cycle. So here the given sine wave has finished 4 periods, right? So it has finished 4 periods here. The next one is frequency. So frequency refers to the number of periods in 1 second. So frequency is always inversely proportional to the period, right? So f equals to 1 by t and t equals to 1 by f. So we know that period means the time required, right? So it refers to the period means time, and time and frequency are always inversely proportional to each other. So a period refers to the amount of time. Similarly, the frequency refers to the number of periods in 1 second. That is simply inverse of the period. Okay. So here the one complete pattern is filled here, right? So here it requires 4 periods, right? The given wave requires 4 periods in 1 second. And similarly, if you want to know the time, that is the period for completion of a one pattern, so t equals to 1 by 4s. Okay. So here the 4 periods require 1 second. That means 1 period requires 1 by 4th second. So this is the time required to finish one pattern cycle. So we know that time and frequency are inversely proportional to each other. So this table represents the time, that is in the format of seconds, and the frequency represented in hertz. Okay, so the 1 second will take 1 hertz of time. So 1 millisecond can be represented in 10 power minus 3 seconds in the time format and 10 power 3 hertz in the frequency format. So here the microseconds, that is 10 power minus 6 seconds. So if we convert it into frequency, then it will be 10 power 6 hertz. So similarly picoseconds also 10 power minus 12 seconds. Right, the time is 10 power minus 12 seconds. And if we take the frequency, that is simply 1 by 10 power minus 12, right? That means 10 power 12 hertz. So frequency and time are inversely proportional to each other. So now let us solve a simple example on period and frequency. Okay, so given that period of a signal is 100 milliseconds, okay, so period is 100 milliseconds. Okay, what is its frequency in kilohertz? So we know that so frequency is the inverse of the period. That means 1 by 100 milliseconds. So how can we represent the millisecond here? So millisecond will be represented in the 10 power minus 3 seconds. So 100 into 10 power, so 1 by 100 into 10 power minus 3 second, right? So that equals to 10 power minus 2, right? So minus 3 and 10 power 2, that equals to 10 power minus 1. Okay, so 10 power minus 1. So that equals to 10 power minus 1. So this is the 10 power minus 1 seconds. So this is the period. So we have converted the, so here given that period of a signal is 100 milliseconds and what is its frequency in kilohertz. So given that period is 100 milliseconds, right? Period equals to 100 milliseconds. So we need to find out what is the frequency. So first of all, we have to convert the given period into seconds format. So it is given in milliseconds. So to convert it into milliseconds, so convert the milliseconds into seconds. So millisecond is 10 power minus 3. So here 100 is 10 square and 10 power minus 3, that equals to 10 power minus 1 second, right? So we know that period equals to 10 power minus 1 second. So now we have to find out the frequency in kilohertz format. Okay, so we know that period equals to 1 by frequency. So 1 by frequency, right? So 1 and frequency equals to 1 by period. So 1 by 10 power minus 1. Okay, so 1 by 10 power minus 1 hertz, that equals to 10 hertz. So but we need the output in the kilohertz format. So that's why we are going to multiply we are going to convert into kilohertz format. For the kilohertz, so we need to add 10 power minus 3. So 10 into 10 power minus 3. So that equals to 10 power minus 2 hertz. 10 power minus 2 kilohertz. So like this format, we are going to convert the frequency. So next one is express a period of 100 milliseconds in microseconds. Okay, so we know that milliseconds equals to 10 power minus 3. So 100 into 10 power minus 3 is 10 power minus 1, as we saw in the previous example. Okay, so now we need to convert it into microseconds. Third parameter of the sine wave is phase. So phase describes the position of waveform related to time 0. Okay, so here the phase means simply, so we are going to find in which direction or in which angle the wave is moving. Okay, so the phase describes the position of the waveform related to the time 0. So here it is starting at the time 0, right? In the graph, QM graph, the sine wave is starting from time 0. So related to the time 0, so in which angle the wave is cutting the graph, so that we are going to consider as the phase. So phase is measured in the degrees or radians, that is 360 degrees is 2 pi radians. So if you observe the given diagram, so here in the first picture, so the sine wave is starting from the related to the position 0. Okay, so that's why it is making 0 degrees. And if you consider the second one, okay, so here the sine wave is starting from the 90 degrees position, right? So it is starting from the 90 degrees position, right? So here the remaining half is negligible here, so it comes under the minus 180 like that. So here the sine wave is starting at the position 90. So 90 degrees it is starting and it is traveling towards the time, right? So that's why here the amplitude is cutting the graph at 90 degrees. Okay, so that's why the phase is 90 degrees for the given pattern. And if you observe the next pattern, so here the wave is starting at the 180 degrees position. Okay, so it is starting at the 180 degrees position. Okay, so that's why, so here the degree for or phase of the given pattern is 180 degrees. And here the time taken for the sine wave here is in the remaining is 1 by 4th of time taken, and the time taken for this sine wave is 1 by 2 of the time taken, that is half of the time taken. Okay, a sine wave with the phase of 0 degrees starts with the time at 0 with a 0 amplitude. The amplitude here is increasing, and here the sine wave with the phase of 90 degrees. So 90 degrees starts at time 0 with a peak amplitude. So it is starting with a peak amplitude, and the amplitude is decreasing here. And similarly here the sine wave with a phase of 180 degrees starts at time 0 with a 0 amplitude, and the amplitude is decreasing here. So the amplitude is decreasing here, right? So in this way, so we are going to see we came to know about the different sine parameters. So the next parameter is wavelength. So wavelength is a property of the signal traveling through the transmission medium. So wavelength is nothing but it is a property of an simple analog signal which is traveling through a transmission medium. Suppose a signal is traveling through a transmission medium. Let us consider it be a fiber optic cable. So the signal is traveling through the transmission medium at the time t, that is at the particular time limit 1 millisecond. So at the 10th millisecond, the wavelength will be traveling towards the other location. So that means the wavelength is traveling in the transmission medium, that is in the fiber optic cable, to the other location at the 10th millisecond. That means the signal position has moved. The signal has moved from one position to another position through the transmission medium. Okay, so the wavelength is nothing but the distance a simple signal can travel in one period. So wavelength is nothing but the distance a signal can travel in one period, that means at a particular time limit. So if you see the formula also, wavelength equals to propagation speed into period. So here wavelength binds period of frequency to a propagation speed. Okay, that means propagation speed into period, and we know that wavelength is the distance a simple signal can travel through the transmission medium in one period of time. Okay, so here if you consider the formula, that is distance equals to speed into time, right? So here we are considering the wavelength as the distance and propagation speed. So speed into period means time, right? So you can consider the wavelength as the distance a signal is traveling through the transmission medium. And here the propagation speed of a signal completely depends on the transmission medium. Suppose a signal is traveling through a fiber optic cable, then it will travel very faster. Suppose if the same signal is traveling in the vacuum, then it will travel at the speed of 3 into 10 to the power of 8 meters per second. Okay, and the propagation speed will be comparatively lower compared to the vacuum in the air, right? So the propagation speed will be lower in the air, and it will be even lower in the cables, and it will be very faster in the fiber optic cables. So actually the wavelength is normally measured in the micrometers or microns. Okay, so instead of meters we are using the micrometers here. So wavelength equals to propagation speed into period, and we know that period equals to 1 by frequency, right? So that's the propagation speed by frequency. We know that signals are of two types, that is the simple signals and the composite signals. Okay, so in the simple signals, the sine wave is generated here. The sine wave will travel. So we know that signals are of two types, that is simple signals and composite signals. So simple signals are also again divided into two types, that is periodic and non-periodic. Similarly, composite signals are also divided into two types, that is periodic and non-periodic. So first of all, what is meant by composite signals? Okay, so here a single frequency sine wave is not useful in the data communications. So we are going to the composite signals, a signal which is made of simple sine waves. In the simple signal, there will be only a single sine wave. But in the case of the composite signals, we are having multiple number of sine waves here. Okay. So normally, the simple sine wave is used in many cases in the real life, such as the single sine wave is used to carry electrical energy from one place to another. Similarly, the single sine wave is used to send an alarm to a security center when a thief opens a door or window in the house. So these two are the simple applications of the simple sine wave. But we cannot apply simple sine waves in all the applications. Suppose if you want to talk with your friend using a phone, then this simple sine wave is not useful at that time. If you are using simple sine wave to make a call to another mobile phone, then it will generate a buzz sound. So that's why we are going for the composite signals. So according to Fourier analysis, any composite signal is a combination of the simple sine waves with different frequencies, amplitudes and phases. Okay. So here the composite signals are divided into two types, that is periodic and non-periodic. So periodic composite signals means the decomposition gives a series of signals with a discrete frequency. Okay. So here the given wave will give a series of signals with discrete frequency. And non-periodic signals means, so it is a combination of the different sine waves with the continuous frequency. Okay, so here the given diagram is of periodic composite signals, so which is generating a series of signals with a discrete frequency. So next one is the bandwidth. In the bandwidth, the range of frequency contained in a composite signal is called the bandwidth. So the bandwidth is normally a difference between the highest and lowest frequencies. Okay. So in the given composite signals, if there is any highest and least frequencies, so we are going to subtract that highest and least frequency to obtain the bandwidth. So in the particular signal, so in the given signal, in the given composite signal, so we are going to consider the highest frequency and the least frequency, and we will obtain the difference between the highest and the least frequency to get the bandwidth. So normally the bandwidth is measured in hertz. Okay, so bandwidth is the highest frequency and lowest frequency of the composite signal. So this is all about the different parameters of the wave, sine wave. Okay, and about the analog signals. So in the next video I will see about the digital signals. Thanks for watching my video. Please do like, share and subscribe to my channel. Thank you.